In last lecture, we have discussed about Hamming window. We started from the generalized part of the Hamming window and then get the Hamming window and Hamming window and compared the same results with rectangular window and triangular window. Today we will discuss another window which is called Blackman window. The important point of Blackman window compared to Hamming and Hanning window, it also involves a cosine as we have seen with the Hamming window and Hanning window, but it involves second harmonic also. This window is an improvement over Hamming window by using second harmonic of cosine in the function. So we can represent Blackman window as WBN equals to 0.42 minus 0.5 cos 2 pi n by m minus 1 plus 0.08 cos 4 pi n by m minus 1 for 0 to n up to m minus 1 and 0 elsewhere. This particular function is causal and valid for both values of m, even and odd. Then by applying the discrete Fourier transform, we can find out the frequency response of the Blackman window is W B omega cos to 0.42 sin omega m by 2 over sin omega by, we are just writing the magnitude part only, plus 0.25 sin omega m by 2 minus pi m over m minus 1 upon sin omega by 2 minus pi by m minus 1. Then plus 0.25 sin omega m by 2 plus pi m over m minus 1 upon sin omega by 2 plus pi over m minus plus 0.04 sin omega m by 2 minus 2 pi m over m minus 1 upon sine omega by 2 minus 2 pi by m minus 1. And then the final term of the equation is 0.04 sine omega m by 2 plus 2 pi m over m minus 1 upon sine omega by 2 minus 2 pi, or it is plus 2 pi by m minus. So we have already seen for a single cosine term we have a two terms in frequency response with this sine, this term and this term for a single cosine term. This term and this term comes from the another cosine term. So involving cosines make our frequency domain representation much more complex to write, but it helps in another ways. We'll just see the properties of this frequency response which we have achieved for a Blackman window, and obviously we'll look for these three properties. First one is main lobe width. As one can see, their number of sine terms increased compared to Hanning window, thus the main lobe width also increases. So in this case the main lobe width is 12 pi by m, which is higher than Hanning triangular window of 8 pi by m. Transition width also approximately equal to 12 pi by m for Blackman window. Second point, peak of side lobe to main lobe ratio. In case of Blackman window, this ratio is minus of 59 dB, which is smaller than Hanning and triangular window. For Hanning window, peak of side lobe over main lobe ratio is minus of 42 dB. Hanning window it is minus 31 dB. Triangular window it is minus of 26 dB. Obviously it is very small compared to rectangular window which has only minus 13 dB. Next point is attenuation in a stop band, which we have also used as a representation AS. In case of Blackman window, the value is 75 dB, which is very large compared to other windows. The comparative table is here, where rectangular window, triangular window, Hanning window and Hamming windows details we have already seen in last lecture. We have now included the Blackman window. One can see the main lobe width in case of Blackman window is higher compared to triangular, Hanning and Hamming window, whereas the suppression of peak side lobe is highest in terms of Blackman window, which is minus 59 dB. Also, attenuation in the stop band is also highest in case of Blackman window, which is 75 dB. Now these 2 points are improved, but this is reduced. Now increment in transition width due to main lobe width can be compensated by increasing the value of M. Now it is very important point. Once we choose a window, we cannot modify these two terms. These are set to be with window function. But we can always modify the transition width or the main lobe width by increasing the value of M. But as the value of M increases, complexity increases. That's mean if we want to conclude this particular point at this instant is if we want to make a filter to have a same transition width as of a rectangular window by using a Blackman window, we have to increase the value of M. To further discuss this point, for same transition width, let's say delta omega dash, to achieve this, if rectangular window is used, then we require M1 length of window. Similarly, if we want to achieve same transition width, then for Blackman window, we require M2 length of window. For Hamming, Hanning and triangular window, M3 is the length required. Then M1 will be minimum, then M3 and then M2. Please note that M2 is related to Blackman window. That means to achieve the same kind of response, transition width response through Blackman window, we have to use higher value of M compared to rectangular window and Hanning, Hamming and triangular window. Now we know the sequence length is important, right, for the properties of the filter, and that sometimes are also referred as order of the filter. Now next we will discuss estimation of the order of the filter. For that particular point, we require certain important aspects such as passband ripple, that is denoted as delta P, delta S as stop band ripple, then omega S, that is stop band H frequency, and omega P, that is passband H frequency. Now order estimation is initially given by Kaiser, also called Kaiser formula, is M greater than equal to minus 20 log base 10 square root of delta S delta P minus 13 over 14.6 omega S minus omega P over 2 pi plus 1. This is also called Kaiser formula. Now the problem with this particular formula is it is not a robust formula and it does not provide correct estimation for all cases. Then we require another formula proposed by Herman, Rabinar and Chan, which states that M is greater than equal to d infinity delta P comma delta S minus F delta P comma delta S omega S minus omega P by 2 pi whole square over omega S minus omega P by 2 pi plus 1. Please note that in case of this formula provided by Herman, Rabinar and Chan, d infinity delta P comma delta S and F delta P comma delta S are the two functions of logarithmic nature. D infinity delta P comma delta S is equal to A1 log base 10 delta P whole square plus A2 log 10 delta P plus A3 multiplied with log 10 delta S minus A4 log base 10 delta P whole square plus A5 log base 10 delta P plus A6. This all A1, A2, A3, A4, A5, A6 are the constants. Delta P and delta S are the ripples in passband and stop band. Similarly, for the function f, of delta P and delta S, it is B1 plus B2 log base 10 delta P minus log base 10 delta S. Please see this case compared to Kaiser formula. In Kaiser formula, we have directly used minus 20 log base 10 square root of delta S into delta P minus 13, which does not provide too much control over the M parameter. But in case of Herman, Ravinar and Chen, there are a lot of terms involved with the log base 10 of delta P and delta S individually with the square and multiplied with different constants. So these two functions provide much more control and thus makes this formula more robust compared to Kaiser formula. Please note that this particular condition which we have discussed in this particular part is only valid if delta P is greater than or equal to delta S. If delta S is greater than or equal to delta P, then simply independent variables will change. That means d infinity delta S comma delta P and f delta S comma delta P. Then everything we have written in this particular formula will be true. Just we have to replace delta P by delta S and delta S by delta P. Now the important point for these two formulas are the values of A1, A2, A3, A4, A5. Similarly, B1 and B2, these all are constants. These all are constants given as this, where A1 is 0.005309, A2 is 0.07114, A3 is minus 0.4761, A4 is 0.00266, A5 is 0.5941, A6 is 0.4278, B1 is 11.012717, B2 is 0.51244. These are the constants directly used for implementation of these functions and to realize the order of the filter. Now, with this particular point, we will end our discussion in this topic. In next lectures, we will discuss some examples using these windows, and then after that, we will discuss Kaiser window, which is slightly different from these kind of windows. That's all for today. Thank you.